The notes for Unit 6, Lesson 4 will cover gas law calculations. So after the notes for this section, you should be able to calculate any unknown variable when using those three main gas laws that we referred to the other day: Boyle's law, Charles' law, and Guy-Lussac's law. So make sure you have your notes packet available, and you'll also want a calculator for the calculations today. All right, so you should have this little table in your notes. So the three main gas laws that we'll start with are Boyle's law, Charles' law, and Guy-Lussac's law. We will add two more laws by the end of this unit, but these are kind of the main three. So you don't have to know which formula represents Boyle's law, but you do need to know how pressure and volume or pressure and temperature are related. So Boyle's law relates pressure and volume. So it states that as you increase the volume of a container, so remember, if you have more space for those molecules to move around, there will be a decrease in pressure. So when you increase the volume, there will be a decrease in pressure and vice versa. So the equation that we'll use is P1 V1, is equal to, try this again, sorry, I'm gonna erase this, is equal to P2 times V2. So what this shows is a pressure reading at a specific volume, which would be P1 and V1, is going to equal a second pressure reading at a second volume, which is P2 times V2. The graph, since this is a inverse relationship, as one goes up, the other goes down, is going to have a little curve like this. So as your pressure goes up, volume goes down, and vice versa. Charles' law relates volume and temperature. So as we increase the temperature of a container or of a sample of gas, the particles are going to spread out and is going to result in an increase in volume. So as one goes up, the other goes up. Since this is a direct relationship, the formula is V1 over T1 is equal to V2 over T2. So again, one volume reading at a specific temperature is going to equal a second volume reading at a second temperature. So I would add this to your notes. The temperature scale must be in Kelvin. And so remember, to convert Celsius to Kelvin, you have to add 273. So anytime you do these calculations, the temperature must be in the Kelvin scale. For the graph, since this is a direct relationship, it's not a very straight line, our graph is going to be a straight line. So as one goes up, the other goes up. All right, the last law that we'll talk about today is Guy-Lussac's law. So Guy-Lussac's law relates pressure and temperature. So as you increase the temperature, now this is assuming that all the other variables are constant. So we have the same sample of gas, we're not adding or taking away any gas particles. And then also, since Guy-Lussac's law relates pressure and temperature, we're assuming that the volume of the container is constant. So as you heat something up, the particles are going to start moving faster, and it is going to increase the amount of pressure that's inside that container. So since this, again, is a direct relationship, the formula is P1 over T1 is equal to P2 over T2. Again, temperature must be in Kelvin. And then since this is a direct relationship, our graph will look similar. Having trouble making straight lines today. Will look similar to Charles' law. So these are the three gas laws that we'll start with. Like I said, we'll add two more in over the course of the next few days. Here is a neater typed version of the notes that we just added. So if you need to pause the video you can do so to make sure that you get all the information. All right, so in your notes, you also have some, oh, I forgot about this part. Before we do our sample problems, as you're reading sample problems, you need to know what unit goes with which variable. So volume is going to be either measured in liters or milliliters. Occasionally, you'll see a centimeters cubed for volume. So those are the main units for volume. Pressure will either be measured in kPa, ATM, or mmHg, and those are abbreviations for kilopascals, atmosphere, and millimeters of mercury. Temperature in the problem will either be given in Celsius or Kelvin, but remember, all calculations, you have to use the Kelvin scale. So even if the problem gives you the information in Celsius, you have to convert Celsius to Kelvin before you solve for the unknown. All right, so now we can start working on these sample problems that are in your notes. So the problem says a given mass of air has a volume of 6 liters. So this is going to be one of our volumes at 101 kPa. We want to know what volume will it occupy at 25.0 kPa if the temperature does not change. So this first number, the 6.00 liters, since it's liters, we know it's a volume. So I'm going to add our given information. kPa, so when we have 101 kPa, kPa is a pressure, so that's going to be our first pressure reading. And then the question says what volume, so the second volume is what we are trying to solve for. Will it occupy at 25.0 kPa? So kPa again is a pressure. Whoops. If the temperature does not change. So in the notebook, we had you put an X through the variable that does not change. So if the temperature stays constant, it's not going to affect this problem. So we only care about pressure and volume. So since we are only given information about pressure and volume, then you have to determine which equation to use. So if you go back, the only equation that deals with pressure and volume is Boyle's law, which is P1 V1 is equal to P2 times V2. So that's the equation that we're going to use. So then you plug in your numbers and solve. So P1, the first pressure given, is 101 kPa. The first volume given is 6.00 liters. That's equal to the second pressure reading, which is 25.0 kPa, times the second volume reading, which is what we are trying to figure out. So if we multiply the variables on the left, 101 times 6, we get 606. The units do not cancel out, so it'd end up being kPa times liters, and that's going to be equal to 25 kPa times V2, which we don't know. So to get V2, or to get our volume by itself, we have to divide each side by 25 kPa. So that cancels out. If we divide over here by kPa, the unit kPa cancels out, and then we're left with liters, which is what we want, because volume, which is what we're trying to solve for, is measured in liters. So if we take 606 divided by 25, we get 24.24. So remember, we have to still round for sig figs. Yay! So when you look at the numbers in the problem, 6.00 has 3 sig figs, 101 has 3 sig figs, and then 25.0 has 3 sig figs. So we're going to round this off to 3 sig figs. The 4 will not round the 2 up, so we're going to end with 24.2. And then like we said up here, liters is the unit that volume will be in, so that would be our final answer. All right, on to the next problem. So as you can see, each step is shown. So step 1, you're always going to record what's given. Step 2, you figure out which equation to use. Step 3, you plug in your numbers and solve. So in this one, the pressure in a car is 198 kPa. So we are given an initial pressure of 198 at 27 degrees Celsius, which is a temperature. After a long drive, the pressure is 225 kPa. So the problem gives us a second pressure reading. And we want to know what is the temperature of the air in the tire. So we want to know our second temperature, and we can assume the volume is constant. So again, volume 1 and volume 2 are not changing, so they are not a factor in this problem. So for our equation, we are only given information about pressure and temperature. So if we go back to our equations, pressure and temperature is here for Guy-Lussac's law. So we're going to use P1 over T1 is equal to P2 over T2. Whoops. All right, so then you can plug in your numbers and solve. So P1 is 198 kPa over our temperature. Now remember, the temperature in the problem is given in Celsius. You have to convert it to Kelvin. So we are going to add 273 to convert this to Kelvin. So if we take 27 plus 273, whoops, my pen wasn't right. We end up with 300 Kelvin. So we have to use the Kelvin temperature. And when you add these, remember the number goes by, yikes, that is really messy. The number goes by decimal places for sig figs. So you want to put a decimal at the end of 300. So both those zeros count for significant figure purposes. All right, so we have P1 over T1 is equal to P2, which is 225 kPa, over our second temperature, which we don't know. That's what we're trying to find. So there's a few different ways you can solve. You can take 198 divided by 300. So we'll do that the first way. So 198 divided by 300, and you get 0.66. Those units do not cancel out, so it's kPa over Kelvin, and that's equal to 225 kPa over T2. And then to get T2 out of the denominator, you would multiply each side by that variable. And then we now need to get the variable by itself, so then we would divide each side by 0.66. So all of that cancels out. So we would end up with, oops, didn't give myself enough room here. We're still dividing each side by that 0.66 value. So the unit kPa cancels out, and then you're left with Kelvin. So if you have 225 divided by 0.66, you get 340.909. So for our sig figs, we would want 3 sig figs. So you would use the numbers that you used in your calculation for your sig figs. So we'd end up with 341 Kelvin. Now another way to solve I'm going to erase this work in the middle that I have. So another way to solve, which some of you are probably questioning why didn't you do this, is to cross multiply. So when you cross multiply, you take your 198, kPa times T2, and then you would take 300 times times 225 kPa. So I'm going to erase this quick to show you that you end up getting the same exact thing. So here we would multiply 300 by 225, and you get 67,500. The units do not cancel out, so it'd be Kelvin times kPa, and that's equal to 198 kPa times T2. So to get T2 by itself, we would divide by 198 kPa. And then kPa cancels out, and we would be left with Kelvin. So we take 67,500 divided by 198, and you get 340.909, which ends up again being 41 Kelvin. So you can solve either way, whichever you are more comfortable with. All right, our final example problem gives us a sample of gas occupies 6.80 liters. So remember, liters is a volume at 325 degrees Celsius, which is a temperature. So remember, for temperature, we have to convert it to Kelvin. So we're going to add 273. So that would be 598 Kelvin, which is the number that would go into the problem. And then we want to know what would its volume be. So we want to know what that second volume would be if we change the temperature to 25 degrees Celsius. Again, we have to take our temperature and add 273. So we'd end up with 298 Kelvin that we would use in the problem. All right, so for this, we are only given volume and temperature. So if we go back to our gas laws, volume and temperature is Charles' law. So we're going to use V1 over T1 is equal to V2 over T2. All right, so then we're going to plug in our numbers. So volume 1 is 6.8. Yikes. Sorry. All right, 6.80. There we go. Yikes, that is hard to read. Sorry guys, 6.80 liters over, and remember we have to use the Kelvin temperature. So 598 Kelvin is equal to our V2, which we don't know, over T2, which is 298 Kelvin. So again, you can cross multiply, or you can solve for the left side, set it equal to the right side, whichever you are more comfortable with. So if we cross multiply, you end up with 6.8 times 298, which is 2026.4. If you do cross multiply, we don't want to round until the very end. So that's equal to 598 times V2. And then to get V2 by itself, we have to divide by 598. So if we take 2026.4 divided by 598, we get 3.3886. And if we round to sig figs, we would have 3 sig figs here, 3 sig figs here, 3 sig figs here. So 3.39. And then our volume, the units have to match the initial values. So since the initial volume is given in liters, this volume would also be in liters. So hopefully this helps. As always, let me know what questions you have.